we have our steps, which is not necessary to memorize or anything. It's just to help. It's just to help if you're stuck and what do I do? You know, that kind of thing. I mean, it's when we get down to here, from there down is just what we did before when we were doing global max min problems. So we've done global max min list of candidate type of problems. But now we're getting into number one, story problems, which makes it harder. And then number two, we're going to get into some situations where the derivative might be undefined. So we got to talk about that. Like a sharp point could be a global max. We get into situations where there's only one candidate. There might not be any endpoint. So maybe we could just do a number line, or we could do some other sort of justification rather than a list of candidates. But a lot of the time it's a list of candidates. So we want to make sure we do that we have those justifications. Now, like Jimmy and I were just talking, like on 22, it was your typical kind of basic problem like we did, like a rectangular box, and you want to have a certain perimeter. And typically that's going to be a square. But I'm not going to probably give you a problem like that on the quiz. There's going to be more to it, so it's not going to come out that easy. But the idea is, even if there was a problem like that, we would want to have work down, we would want to justify, we would want to go through this process, because that's what we're really talking about. How can we use the calculus to get these things? So if, you know, the above the red line, you know, that's where it can get tough. Like that's where 17 is so hard, right? I mean, hopefully below the red line, that's not difficult, right? I mean, it's the same thing. Do the derivative, see where it's 0. Do the derivative, see if it's undefined. Put those into those stationary points, those critical points. Plug those back into the original function that you're trying to maximize or minimize. See which one's the highest, see which one's the lowest. That's it. I mean, endpoints, your list of candidates. So below the red line, I hope, and you're going to get to use your calculator. So if it's a tough derivative, your calculator can do that. You got to plug numbers. You got to solve a tough equation. Your calculator can do it. You got to plug those values into the original function. Your calculator can do it, right? So my hope is below the red line, that is not difficult, right? So if a problem is easy to set up, that's the part above the red line, then the problem should be easy. We should be able to do it, right? So as we do these optimization type story problems, probably what I hope would be the new part that, for us anyway in here, is getting them set up into what we're trying to maximize or minimize, okay? So let's talk about it. So here's number 4, okay? Now, I went ahead, and this is where I was talking about with pictures, right? Not every one of them, but a lot of these problems had described some situation that could be done with a picture, so I think that's helpful. So look at what I've got in number 4. I've got D. What does that D stand for? Distance, right? Because that's what we were trying to do, is minimize the distance. If you read that problem, right, and step 1 is identify what you're trying to optimize. So in that problem, it said find a point on that line, y equals negative 2x plus 2. Find a point on that line that is closest to the point 0, 1. Right? So I graphed that line, and I just put a point on there. I called it x and y because I don't know what it is. And I want to find the point that's on that line that's closest to the point 0, 1. So I'm trying to minimize distance. So right away that tells me write down D equals. Right? That's what it's going to be called, that I'm trying to minimize. Okay, well, I need to do a distance formula. So I'm going to take and subtract my y's and square it, subtract my x's and square it. That's how you find the distance. You got to know it, right? I mean, you got to be able to pull it in these various equations and things you need. So that's what I'm trying to do. Now, it's got 2 variables in there. It's got an x and a y. Do I have something I can replace the y with? This right here. Y is equal to negative 2x plus 2. As a matter of fact, we're going to do a number problem. Shanghai problem is the same way, where we're talking about some unknown point on a curve or a line or whatever. Some people were asking me in the parametric thing where it talked about a curve, it turned out to be a line. Well, a line is a curve in that sense, right? Like when they say graph this curve, this equation represents a curve. I mean, technically that could, you know, in that context, a line could qualify. But anyway, when we have an unknown point, call it x and y, but if you have the equation of that, graph, then a lot of times I'll just write it this way. I won't even write it x, y. I'll just write it x, comma, negative 2x plus 2, right? That helps me to eliminate any value there. I mean, if I had the graph y equals x squared, right? I had a parabola like so, and I want to label a point on there. I could label it xy, but I could also just label it x comma x squared, right? Because that's what the y is. The y's are x squared. All right. Oops. All right. So anyway, back to this. So I'm going to replace that y with negative 2x plus 2 minus 1 squared. This would just be x squared. Now I could simplify that a little bit. Plus 2 minus 1 would just be plus 1. So that becomes that. Now at this point, since I've got my calculators, I'm not going to simplify that anymore. I'm just going to type that into my calculator probably. Let it give me the derivative. It's some ugly mess of a thing. Well, what the heck. You guys get your calculators out. Let's do it. Type that into your calculator. You could simplify this if you wanted to, but that would probably be work that is unnecessary. You would need, if this were the quiz, you would need to write down what d prime is. So let's go ahead and do it. Yes. Yeah, go absolutely. What are we getting for d prime? Somebody want to tell me? It's something over something, I think, isn't it? And there's going to be a square root down here. So what would he get? 5x minus 2. Okay, and we're going to set that equal to 0. Now, this is a great problem. This is a great example right here of, because it's a fraction, of finding the critical points. We're interested in now when the derivative is 0 and when the derivative is undefined. Well, when is this derivative going to be 0? A fraction is only 0 when the top is 0 and the bottom's not, right? Like 0 over 4, 0 over 5, 0 over 6, something like that. Because we don't want to get 0 over 0, right? And so we can test them. I don't think that's going to happen. Typically, that doesn't happen in these problems. So when the top is 0. So all we care about is that. That's all we have to do. Now, yeah, you could do a solve right now. You could go solve. You could type that big mess in or grab that big mess. But to be honest, what would be smarter probably is just go solve 5x minus 2 equals 0. Well, that's so easy you could do it without even the calculator, but that's at 2/5. Or if you like a decimal in this problem, you'd rather do 0.4, that's fine. So you can take that whole derivative, set it equal to 0, and do a solve, but understand, we only care when the top is 0. Now, what about undefined? You can't, on your calculator, ask the question, when does this equal undefined? You can't do that. Well, when is this undefined? When's a fraction undefined? When the bottom is 0. So now we can do a solve, and the square root doesn't matter because square root of 0 is 0. So just do the inside. So do a solve right now, and do 5x squared minus 4x plus 1. See when that is equal to 0. You can't forget about this part. You've got to have this on your paper. And don't just always write d prime's never undefined, because sometimes it is undefined. But maybe it's not. I don't know. I don't remember on this one. Equals 0, yeah. So you would type in 5x, in a solve, you would do solve, 5x squared minus 4x plus 1 equals 0, comma x. Say false. So what that means is it's never undefined. So d prime undefined, never. Okay? But you can't forget about checking that. So you would need to take the bottom and set it equal to 0 and see if it ever is, because that would be a potential candidate, because it might be like a sharp point that could be an actual candidate. Are there any endpoints here? Now, what do we mean by endpoints? Again, let's say this again. This is always something that's tricky. What are endpoints? Ends of what? What values up here? I got D's, I got X's. That's about it, I guess.
The values of X that we care about.
The values, okay, you're partly right. The values of X, the endpoints are the values of X, the input, whatever the input is, it's X here, that are what? The littlest that X can be, and the biggest that X can be. I mean, I don't write that down in your notes and put big stars around it, write it on one great big page maybe so you always never forget it. Endpoints, when I ask what are the endpoints, what should be going through your mind is it's whatever your input is, it's the littlest it can be and it's the biggest it can be in this scenario. So for us, it's X. Well, that's on this picture, right? It's this X right here. It's this dot that's on this line. Well, what's the littlest that X could be? Negative infinity, right? This dot could be way out here. I mean, can't see enough of my line to know, but if I go way out here to negative infinity, there's going to be a point on this line, right? There's going to be a point on this line. It could be way up here. Now, is that going to be the closest to that point? No way. What's the biggest X could be? Positive infinity. It could be way out here. Is that going to be the closest? Okay, so back here on my notes, it says, number 6 says, use list of candidates or number line or some justification to identify a max or a min. So if you've drawn a picture, you could actually not do a number line, not do a list of candidates here. You could simply say the only candidate is when X equals 0.4. And according to this picture, if X is towards negative infinity, those points are getting farther away from 0, 1. When X goes to positive infinity, they're getting farther away from 0, 1. And so at 0.4, that will be the point that is the closest to 0, 1. So a paragraph almost, a sentence or two, could tell you the answer to this. Now, what did it say? Did it say, what is the distance? Or I don't know what, the last step, 7, is to actually answer the question. Right? What was the actual question?
Which on the line, y equals negative 2x plus 2 is closest to 0, 1.
So, 0.4 would be the X coordinate. How would we get the Y coordinate? Plug it into this equation up here. So negative 2 times 0.4 would be negative 0.8 plus 2 would be 1.2. So there's the actual answer to the question. So we can't forget that. But there needs to be some justification of why that's the minimum. So a sentence or two in this problem could do it, right? Because points out to the left and right on this line are going to get farther and farther away from the point 0, 1. So look at the picture. The point 0.4 that we just found is going to be the closest, okay? Now, you could do a number line, though, right? We could do a D prime number line. We said if you only have one candidate, a number line could be good. So I could put a 0, I could put a 1, I could plug that into my D prime. Here's my D prime right here. We know the bottom's always going to be positive because it's a square root, right? And we know it's never 0. We already found that out. So the bottom's always going to be positive. So all I really care about is the top. So I put a 0 into here, I get a negative. Put a 1 in here, 5 minus 2 is positive. So what do you got? D prime, since remember the word always? So if I was going to do a number line here, I would say D prime is always negative before 0.4, so D is always decreasing, and after D is always increasing. So therefore 0.4 is a minimum. You could do that, okay? Somehow you've got to have that justification. So as I was looking at your homework, as I was going around, I saw a lot of work, I saw a lot of equations and stuff. I didn't see a lot of explanations maybe, or maybe it was list of candidates, maybe you did that. Okay, but anyway, okay. What would a list of candidates look like? I suppose you could have done this. We talked about this yesterday. For your endpoints, you could have talked about negative infinity, and you could have talked, I have trouble with infinity. positive infinity. And then I could have done D of 0.4. So if you really wanted to do a list of candidates, you could, right? So you could say, okay, what is D doing as you go to negative infinity? Well, here you're going to square it. So that's going to be positive infinity plus infinity. You square it, that's infinity. So as x goes to negative infinity, you're getting infinity, right? They're getting farther and farther away, the distance. This one's going to infinity. Okay? What about 0.4? You plug did anybody plug in a 0.4 into their distance equation? Okay? Well, you're going to get some number here. How far away it is, right? You're going to get some number. And that's clearly your minimum because that's going to be smaller than infinity. So you could have done list of candidates as a justification. So you have some leeway in some of these problems. But one way or the other, you've got to do step 6 to justify, okay, to show that you're thinking about why this is a max or a min, and then, of course, always answer the question, which in this case is what are the coordinates of the point. But it might have been distance. It might have wanted to know how close is that point. So you might have had to have that in there too. Okay, let's go to number 9. Now, number 9 I pretty much have up here. We're not going to spend hardly any time on that because it's just like the one we did in class. Exactly like the one we did in class. Product, you got two numbers that add up to 10. I think the one we did, they added up to what, 18? So, I mean, it's exactly the same problem. So I call it P for product. So we solve this one for y, we substitute in, we get this, we do the derivative, set equal to 0. It's never undefined. 5 is the thing. I can do a list of candidates, you know, and so 5 and 5. 5 and 5 was going to give me the largest product. So that's that whole square idea. It's a lot like number 22. Okay, let's go to number 11. Now, here's one of the problems I see with 11. It says in the reading of the problem, it says, what is the minimum value of this expression? Just a weird way of writing it tends to throw people off. So it wants to know the minimum of this, and then what did it tell you? The two numbers add up to 4. Oh, it just said x plus y is equal to 4. And what was it? X had to be greater than 0 or y?
X.
X has to be greater than or equal to 0. So x got to be at least positive. So we want to find the minimum value of this. So what am I missing here? What's missing here?
The sum.
Well, right, but I mean in my setup. Something to call it, right? Something to call it. This is why it makes such a big deal about this. That's why step 1 is identify what it is you're trying to minimize or maximize. We're trying to minimize distance, so I called it D. Here, we're trying to maximize this product, so I called it P. Here, they just said minimize this. We got to call it something. What should we call it?
I did M.
There you go. Why M?
Oh, forget.
Okay. Minimum, you're going to minimize it.
Oh, that's why.
You're going to minimize it? Sure. Call it M. I don't care. Call it M. Call it something. That's just it, right? We got it so we can do M prime, right? Because that's what we want to do is M prime. Okay, once you get over that hurdle, isn't it just the same thing we've been doing? Right? Or are you just going to solve that, right? So you can get in terms of one variable. So you're going to have x cubed plus 4 minus x. So now we need M prime. So that's 3x squared. That'll be 0 minus 1. Set that equal to 0. What do we get? Plus or minus root 3 over 3.
Yes.
But didn't it say x had to be positive? So we can't have negative. So root 3 over 3. Okay, we can solve that on our calculator, or we could just, it's a pretty easy one. So again, one candidate. Do we have endpoints?
0.
X could only be 0,
But
can't be negative.
it's infinity, which for that.
Interesting. Now wait a minute. Is it infinity?
It has to be you equal to less than 4.
I was going to say, because if x is, oh wait, no, did it say y? Had to be, couldn't y be negative?
No, really. Never saw.
Couldn't this be 7 and negative 3? Wouldn't that be 4? Can y be negative?
Yeah.
It doesn't say.
I think y can be negative.
Yeah.
So I don't think there is another endpoint, is there?
No.
See what I'm saying? I don't think it can be. They didn't say y couldn't be negative. So x could get bigger and bigger, and then that would just make y get more and more negative, right? So I do not think there is a right endpoint, right? And it's one of the reasons I picked this problem, actually, so we could look at that scenario, right? So there really is, I mean, it's really infinity, so it's not really an endpoint. You're right. Technically, that would be that, okay? But in my list of candidates, I could talk about that. So I could go, I'm going to look at m of 0. I'm going to look at m of root 3 over 3. So at least I do have two candidates. So as long as I have more than one, as long as I have two of them, I can do a list of candidates. And I probably should consider what happens as x gets bigger and bigger, right? What happens as x goes to infinity? So a list of candidates would be a good idea here. And what about, oh, I must have called it E at one point when I worked this. I don't know why I have an E there. I think I must have. I don't know why I would have called it E either. But is m prime ever undefined? Here's m prime right here. Never undefined. Okay? So m prime is never undefined. So I don't want to forget about that. All right. So now we're going to plug that in. So I'm going to put 0 back up here into m, and I get 4. Okay? Let's put root 3 over 3 into there. Anybody got that yet? Root 3 over 3 cubed plus 4 minus root 3 over 3. Let's get a decimal so we can. How much? 615. As x goes to infinity, what's happening to this? Isn't it getting bigger and bigger and bigger? The x cube's going to dominate this. So as x gets big, this is getting really big. And we were looking for minimum, right? So there it is right there. There's our minimum. So yeah, what's the question?
What is the minimum value of the expression?
Okay. So the minimum value is 3.615. So the answer, there's no units to put on it or anything. So the minimum value is 3 points. So be really clear about what your answer is. You got all this work and stuff that I want to see. Be really clear. When you answer these story problems, be really clear. Put a big box around it, stars, colored pencil out, whatever. This is my answer to the question. Okay? All right. We'll skip Shanghai for a minute. Go to number 22. Won't spend much time on 22 because 22 is just like number 9, right? You were supposed to, part A, you're supposed to find the max area, right? Area of a rectangle, x plus y. The perimeter is 40. So 2x plus 2y is 40. Y equals 20 minus x. You substitute that in for the y. You get this, upside down parabola, do the derivative. A prime never undefined, right? Undefined never. Okay, x equals 10. Voila, it's a square. It's a 10 by 10. So the max area would be 100. And then part B is just the reverse of that, right? The reverse of that. In other words, now you're trying to maximize the perimeter. So 2x plus 2y, and you're given what? The area is 100. So x times y has to be 100. So what would I do with that information? Solve for one of those. Makes it just a little messier, but it's still the same thing. So we have 2x plus, and then we would have, what, 200 over x? Y would equal 100 over x, so I would substitute in there 2 times that would be 200 over x. So I do my derivative. Now you're going to have maybe a place where p prime is undefined, possibly, which is when x is 0, but it's not going to be that. It ends up being a square again, right? Ends up being a square, but that's part C. Part C is what is your result of those two things tell you. Anybody have a question on the rest of this? With the x on the bottom, obviously you're going to get a negative 2 power in your thing, in your derivative when you solve it, but it's the same process. Okay? Same process. So, all right. So that's 22. So let's talk here about Shanghai. Okay, so all right. Saw some of you with a picture similar to this in your on your page, and that's good if you got that far. Okay. Let me. I got a picture here. I want to. No, I don't want that picture. That's not what I want. I want. Okay, that must not be where that is. Give me just a second. It's not there. I should have looked up this ahead of time. I meant to. See one that says Shanghai? Oh, here it is right here. It says Shanghai. All right, here's what's going on. Okay, it talked about the parabola 1 minus x squared, and let's be a little more specific here about the wording. Okay, so it says that consider the part of a parabola from -1 to 1. This curve fits snugly inside an isosceles triangle. Okay, so there in the yellow is our isosceles triangle. Okay, so 1 minus x squared, notice it crosses the x-axis at -1 and 1, so that's what it's talking about there. And snugly means what? That the sides of the isosceles triangle are touching, let's use a more exacting word, tangent to the parabola, right? Touching at one point. And so then the question is, find the point where it was. Is that what it was? Find the point or find the area? What is the smallest possible area of such a triangle? So if you look at this, and this is what's nice about this program, is I can look at the variations. See how the area is getting bigger here? 14 something. And as I slide this point down, the area is getting smaller. But then what happens? At some point, it starts getting bigger again. Right? This is what we're talking about. There are a series of triangles here. They're getting smaller and smaller until at some point on here it's the smallest. Okay. Step 1. Identify what we're trying to minimize or maximize. What is it? Area of a triangle. Right? Step 1. Identify what we're trying to minimize or maximize. We're trying to minimize the area of a triangle, which is 1/2 its base times its height. Okay? Step 2, and I told you I should have had to draw a picture there in my steps. But step 2 was, write an equation for that. Well, I've already done it, right? That's what I did. Somehow write an equation. Step 3 is the really tricky part, right? Step 3 is where all the work is in this. Well, there's plenty of work after, but then we can just use our calculators, do the derivative, set it equal to 0, find the list of candidates, blah, 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 all that stuff, right? We can do that, especially since we got our calculators to do it if it comes out to be a hard equation, right? But how do we get this? An area equation is just one variable, okay? So here's my picture. So you saw the picture we had up here, okay? So this is why later on, whenever we run into a problem like this, we'll talk about it being the Shanghai problem or the Luke Skywalker problem. Later in the week, we're going to do a similar problem. It has Luke Skywalker in it. So sometimes we call it Luke Skywalker. It depends if you're a big Star Wars fan, you call it Luke Skywalker. Or Shanghai, whatever. This is the first time we've run into a tangent line situation where we didn't know the point where it was tangent, right? Up until now, I said, hey, tangent line, write the equation of tangent line, that should be easy. They give you the point where it's tangent, and then you have to do the derivative, find the slope, and you got it. Well, now we're talking about a tangent line, but we don't know the point where it's tangent. That's the Shanghai problem. That's the Shanghai problem. You got a tangent line, and you don't know where it's tangent. Okay, so what do we do to do the Shanghai problem? Well, we need, and here's the secret to the Shanghai problem, write down at least two, in this problem we actually need 3, but most of the time in the Shanghai problem you only need 2. Write down 2 ways to do the slope of the line. Write down 2 ways, so if you want to make a mental note to yourself here, key to the Shanghai problem is writing down 2 different ways to describe the slope. Well, the two ways are your algebra 1 way, which is slope between 2 points, and then your calculus way, which is derivative. So down in the bottom right corner, now you can see that I've labeled the triangle here a little bit. So what I did, and that's a big part of these problems too, is just proper labeling. So I said, okay, I don't know where it's touching the graph, so I'm going to call that xy. Because remember, I do know the equation of the parabola, and so that's what x and y are, points on the parabola. Now you might say x and y are also points on the line. Well, I can't use x and y to mean two different things, right? So x and y in this problem are going to be points on the parabola. That's what x and y are. So right here, this point on that line is also on the parabola, so I can call it x and y. Now, that triangle is going to touch up here somewhere, but I don't know where. Because as you saw in that other picture, as I slide this point, that's going to change, right? So I don't know where. Now, this is 1 right here. But the triangle is going to touch up above that, right? Same thing down here. This leg of the triangle is not going to touch here at 1, right? I mean, it could, and then, but you're going to have, as you saw, it's going to be a really big triangle then at that point, right? So it's probably in between here somewhere, but it's probably going to touch out here somewhere. And the farther up here I get, the farther out here that touches. Now, I called it B. Why did I call this B and H? Yeah, that was my idea. But now, B is actually measured from where, though, on this picture? From the origin, right? So that's actually, so B, in my picture, B is actually there, right? So what's the base of my triangle actually then? 2B. 2B, right? So this B here is different than this B over here, right? When I made up this, I wasn't thinking of my picture yet, right? So we got to keep that in mind, right? So, at this point, I would probably throw that out and I'd say, okay, for this triangle, it's 1/2 the base, which is 2B, times H. Would that be true? So for this particular triangle I have here, this is actually my area. B times H. Everybody okay with that? Now, I guess I could call this, what could I call this right here? Instead of B? Half B, right? I could say, here's my base. I could call this half B. But then my problem just gets more complicated. So I like this because now I don't have fraction to deal with, right? So I'm going to go ahead and call that B. I'm going to call that B. Okay, so little things like that you have to always kind of think about when you're doing it. All right, so step 1 and 2 is identify and write an equation. So I got it, but it's still no good because I only have I still have 2 variables, right? I want 1. So here, again, back to this now. The secret of the Shanghai problem is write at least 2 different ways to do the slope. Well, one way to do the slope is a derivative, negative 2x, right? Because that's what the slope of that's what derivative is. It's the slope of the tangent line, right? So it's negative 2x. So that's the slope of this line. Another way to do the slope of this line is slope between 2 points. So let's pick these 2 points right here, right? So y minus 0 and x minus b, right? So that would be the slope of this line. And now let's do it again. Now, why are you doing it so many times? Well, you'll see here in a minute. Okay? And so let's do this one. Now, I chose to go this way. Y minus h and x minus 0, right? So all 3 of these should be what? Equal, right? They all represent the slope of that line. Every one. So I should be able to, let's take this first one. Y over x minus b should be equal to negative 2x. Right? Now you might be looking at that and say, okay, what's that doing? Now remember, what am I trying to do here? I'm trying to get this in terms of just one variable. Well, usually that means getting another equation, solving it for one variable, and substituting it in. You see what I'm saying? That's what I'm trying to do here. So what if I would solve this for b, is what I'm thinking. Now, so then I got this y in there. Is there something I could replace that y with? Isn't y equal to 1 minus x squared? Yes. See, I could have done that right from the get-go. Instead of putting x comma y here, I could have put x comma 1 minus x squared, right? Probably would have normally, but people don't always see that right away. They always put x, y to start, so that's why I did x, y. Okay, so in place of the y, I'm going to put 1 minus x squared. Now, couldn't I, and this is what usually happens in Shanghai. Usually we don't have 2 points we don't know something about. A lot of times with Shanghai, we don't know where it's touching the curve, but we do know another point on the line somewhere else. Like maybe we knew this was 0, 5, or we knew this was 6, 0. So if that was the case, we would have like a 6 here, right? And then we'd be in good shape, right? We would be able to just solve for that and go. But we're going to have to do this. So right now I can solve this for b. Now your calculator actually do this, right? You know how when we do a solve? We do a solve and we do an equation, we say solve for x. You can type that equation right there and tell it solve for b. Let's do it. Let's put it in your calculator. It's not very hard. I mean, we can do it with algebra, but what the heck? We got our calculators here, so let's do it. Let's do a solve on this and tell it to solve for b. And then what I'm going to do is I'm going to stick that into this equation in place of b. Emily, what do you got?
3x squared minus 1
That's it?
over 2x.
3x squared. For some reason that didn't work.
I got x squared plus 1 over 2x.
Yeah.
Two
Say that again.
x squared plus 1 over 2x.
Did you have a plus somewhere instead of a minus? Maybe or something.
Oh, I probably mixed up the negative.
Okay, so now I'm going to replace that b with that. Now you might be saying, okay, that didn't get you anywhere because you had 2 variables, b and h, and now you still got 2 variables, x and h. Right. That's why we needed to have another one down here, right? So I can now do the same thing for h. I can now take this and this, the top and my bottom one down here, right? Because they both, again, this is the key to the Shanghai problem. The key to doing this is we've got a line with 3 points on it. There's many different ways we can write the slope of that line. The key is one of them is derivative, and the other one is slope between 2 points. So now I'm going to take my bottom one, y minus h, over x, and I'm going to set that equal to negative 2x. Remember, negative 2x is my derivative, and derivative means slope of the tangent line. Now, in place of y, I'm going to put what? 1 minus x squared. So I got 1 minus x squared minus h all over x equals negative 2x. Now, in your calculator, type that in and tell it to solve for h.
Yeah, x squared plus 1.
That's it, right?
Yes.
Just x squared plus 1. Okay? Now, all of that work was just to get through step 3 in our list, right? So that's what I was talking about is the problems vary in difficulty depending on how hard the first 3 steps are. Because once you're there, that was like the red line I had in our list. Once you're to the red line, then it's all the same. Now it's just find them. Now what we haven't written down is endpoints. And of course, and the answers are in the thing here, and I'll show you what that is. But what are my endpoints? Well, it'd be, what's my input variable? X. What's the littlest x could be? No. Where's x? Look at my picture. The littlest x could be? If it goes over here, then you just got the same picture, right? So the littlest x could be would be 0. Now you wouldn't even, actually if it's right at 0, what's your tangent line? It's horizontal, isn't it? Would you even have a triangle? No, it'd be an infinite area. Is that going to be a minimum? No, but 0, okay? So the littlest x could be would be if it's right up here, and the biggest x could be would be 1, right there, right? Can't go down here, right? We were, that it didn't, right? It said it's got to be, it said the triangle was above, between the x-axis and the
That'd be snugly.
right, snugly fit. So so our endpoints, our endpoints are 0 and 1. Okay? So now you're going to do the derivative, you're going to set it equal to 0, your calculator can do all that and solve and find your stationary points. You're going to have a list of candidates. Let me change this so we can see it. So you're going to have a list of candidates. So you're going to do a of 0. Well, that's going to be a problem. That's why you're going to get infinity here. Look at this, everybody. When you plug a 0 back into the original, you're going to get 0 on the bottom. Well, what does 10 over 0 mean? It means infinity, right? We've talked about that. That's what we were just talking about, because you're going to get that horizontal line at the top. And so that's essentially going to be an infinite area. You're going to have a of 1, which is whatever that area is. And then I think, let me look it up here real quick. What was this, number 17? And they got root 3 over 3, it looks like. Root 3 over 3 is what they got for when you solve this. Okay? That's what the back of the book says. And you're going to plug that in. And decimals would be nicer probably for the final answer, but they've got 8 root 3 over 9. When you plug that into here, you get 8 root 3 over 9, whatever that is as an answer. And at 1, if you plug 1 in here, that's pretty easy. 2 over 2, that's 1. 1 plus 1 is 2. So you get 2. Okay, and this must be smaller than that. Okay, so there's your minimum area, right, to answer the question. So again, once we get it set up, it is not hard, right? You got your calculator, you do the derivative, set it equals 0. Is the derivative ever undefined? I think it is at 0. I think it's undefined at 0, but we already have that as an endpoint. So that's in our list of candidates, so the derivative is undefined. I think once you do the derivative, you'll see the bottom, if the bottom is 0, so x equals 0 is undefined, and so boom, 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 go through those steps, right? So, very hard one because it was hard to set up. You look at 22, very easy one, should be, as we go through, because it's just really easy to set up. And number 11, they set up for you. You just had to call it something like M, and then, I mean, it was pretty much just there, right? And then you just go through those steps that we've done before. All right, what do we want to add to this? Well, not a lot. We want to practice going through the process and getting comfortable with it so they do feel like they're easy when you get to those. So let's go. Let me hand this thing out here, and I just want to talk about a couple of terms, and I want to get you started on one of the homework problems, and then let you start working. Okay, this is a packet of business applications. If you are a business major and you have to take applied calculus, that would be the one calculus class they would probably sign you up for. I know when Ryan went last summer at enrollment in business, what I was thinking of, that was their first thought, was to enroll him in the applied calculus class, the business calc. And that's fine. That's what you would take. That's the only one you need. And so you would do a lot of this. Now, our book doesn't have many of these applications, so I pulled these from another book. So that's what this packet is. I just call this on the homework, it's called the business packet. Okay? So if you look through here, I want to go to page 216 in this packet. And it's got a little table there, summary of some terms. Okay? All right. So some terms that we need to know from a business standpoint. Obviously, profit. Now, profit is equal to your revenue minus cost. Revenue is money coming in and cost is like expenses, that sort of thing. So money coming in is typically number of units sold times price per unit. I mean, it's pretty common sense, right? I mean, you sell 1,000 units for $10 each, you got $10,000 coming in. But that's not your profit, that's your revenue, right? That's the money coming in. You have to subtract off your expenses, how much you had to pay your labor, how much your overhead was for rent on the building and electricity to run the machines and whatever, right? Labor, did I say that? Yeah, labor, how much you pay your people, right? Cost of materials, right? All of those things would be rolled into the expenses, okay? So profit, so many times we're trying to find the max profit, right? The max profit. Now sometimes it's just max revenue. Some questions will just ask for the minimum cost, okay? So, you know, those would be different things that you could be asked to do. Now, a couple of other terms. P prime is, the term for that is the marginal profit. The marginal profit. Now, so in business terms, they'll talk about marginal profit being zero. Well, think about that. Is that a good or bad thing for marginal profit to be zero? Is it a good thing for P prime to be zero?
No. Depends on what the.
What if that was the P graph right there? What would P prime be right there? Zero. Would that be a good spot right there on the profit graph? This wouldn't be a good spot on the profit graph. That would be the spot. That's what you want. The highest profit, right?
In terms of time.
Yeah, in terms of time. Well, no, not time. It depends. Probably number of units. X is probably number of units. I'm sorry, I see. So you're saying, so as time is going on, your profit went up and then went down. But I'm talking about this point. So at this point, if this was time, would this be a good place to be? In time, yeah, that'd be a good place to be. But actually, the X typically is units sold, right? Units sold. So that's where you would want to be. You would want to figure out how many units, right? Now, if you sell so many per day, then that could be days too, right? I mean, it could be time. But typically, the X is units, okay? Yeah, typically X is units. So that's where you'd want to be. So marginal profit zero is usually where you want to be. And they say it could be a minimum, right? You wouldn't want that, right? So, but typically that's what you're looking for is marginal profit zero. So if marginal profit is positive, what's that tell you? What's increasing? Profit, right? If marginal profit, look what I got there. If marginal profit's positive, think of the chart. That means P prime is positive. If P prime's positive, P is increasing. So your profit's increasing. Is that good?
Yeah.
Well, it's better than decreasing, but is it as good as P prime being zero? No. So in other words, if the marginal profit's positive, what that means is keep producing more units, right? Let's make more, because our profit's still going up. So let's make more. If P prime's negative, maybe we're on the other side, right? We're making too many. In other words, maybe they're not selling, right? We're making too many. Maybe they're not selling. It's driven the price down. We've made too many of them. They're too easy to get, so the price is going down, right? There'll be a lot of things why that might be happening. Maybe we had to open up a new store and hire more people, right? And now that's costing us too much. And so our profit's going down. So they talk about, so a business person wouldn't talk in terms of derivative, right? They wouldn't talk in terms of P prime. They would use the term marginal profit. Marginal profit is zero. That's a good thing, or close to zero. That's a good thing because that's near the max. Okay? Marginal profit negative is a bad thing because it means your profits are going down. That's the terminology they would use. Same thing with marginal cost and marginal revenue. So R prime is considered, that's marginal revenue. Okay? And C prime is marginal cost. So when you hear those terms, it means derivative. Okay, and that's in that little table there on the right side of that table. Okay, and I think everything else there, I guess the only other thing would be that C bar. C bar is another term they use a lot, and that is cost per unit. So that would be just the total cost, C, divided by X. Right? C bar is the total cost, and then you just divide that by how many units, and that's your cost per unit. So sometimes they might want you to minimize C bar, right? They want to minimize the cost per unit. So you're trying to minimize your cost, whatever that equation is, divided by X. Just take your cost equation divided by X. Okay? All right. So those are some terms. We're going to do just a couple of simple problems out of this packet. They're really simple to start with, but just getting used to those terms, okay? But we also have a few in our homework, in our book we're going to do. So number 28, if you look at your next homework assignment, number 28 is one of the problems. It's got multiple parts to it. So we're going to start by working together 28B. 28B. I'm just opening up my books. I'm not looking at your guys. This is in the book. This is in our book. Okay? So, we're on 4.3, day 2. You got 19, 21, 27, and 28 in our book. And then the business packet, we've got number 3 and number 8. Okay, is what the assignment sheet says. All right, so 28's got multiple parts. Let's look at them here. All right, Federalist Express. We don't want to violate any copyrights or anything, I guess. Federalist Express limits the size of a mailable parcel. The longest side plus the girth, which is the perimeter of a cross-section perpendicular to the long side. The girth may not exceed 108 inches. And part B says, find the dimensions of the mailable parcel. We're going to skip part A, by the way. Find the dimensions of the mailable rectangular parcel with a square base that has the largest volume. It says, hint, consider 2 cases depending on which side is longest. Okay, so we're going to try to mail a rectangular box, basically, that has a square base. Now, so the first one that comes to mind when I think about drawing this would be something like this. Okay. Now, it said it was a square base. That's key to this, because otherwise we'd have 3 variables, and that would make this a lot harder, right? So making it a square base makes it a lot simpler. Okay? So what can I call the height here? What do you want to call this right here?
H.
H?
Yeah, I need to be creative.
I'll go with Y just because I chose X for the other one. But yeah, length and width, or length and height, you can do H there. I don't care. Doesn't matter. Doesn't matter. Now, so there's a whole sentence in there about girth and perpendicular, so we'll get to that in a second. But step 1 is identify what you're trying to minimize or maximize. What is that here? What are we trying to minimize or maximize? We're trying to maximize the volume of this figure. So what is the volume of this figure? X squared times what? Length times width times height. X squared times what? That's what we're trying to maximize. Now, let's get into this thing about the 2 cases and the girth and all that stuff. They have a limitation because what they're saying is, my guess is they would mail something if it doesn't fit this, but it would probably cost extra because it would be oblong and weird shaped, and that might not fit in their truck as easily, so they might charge extra for strange types of packages. That's basically what this is saying. Okay? So, the perimeter of a cross-section perpendicular to the long side. Oh. So what's the long side in my picture?
Y.
Y. So what would be perpendicular to Y?
X.
This way. So the perimeter perpendicular to this. So wouldn't that be
X.
this? Isn't that the girth? Right? Kind of like me. I'm standing here. Here's my long side. The girth would be like a round, which is getting to be more of a maximum all the time. But anyway, that's what I think when I think of girth. I don't get on scale. All right. So that's what we'd be talking about. But why would there be possibly two cases, two situations?
Because your long side could be the X.
What if the long side is the X? What if we had a more of a flat kind of a box
Jeez.
that looked more like this? Right? Apologize for that. Right? Now where's the girth?
Y.
Perpendicular to the long side. Here's the long side. Perpendicular to that, wouldn't that be across here? So it would be this perimeter here, which would be what?
2y times 2 or plus 2x.
So it'd be x here and x here. That'd be 2x. So it'd be 2x plus 2y. What did it say that had to be? It may not exceed 108. So is it necessary to put less than or equal to 108? I would say no. What do you suppose the largest volume would be? If we use all 108 inches were allowed, right? So I would say we do not need to say less than or equal to. I think we can say, hey, the largest volume is going to be if we go right to the tip of what they're going to let us do. So in this problem, the volume is still x squared y, right? But my secondary equation, the one I'm going to use to get the y out of there, is going to be that. What was it in this one?
X times 4.
X, 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 and X, right? 4x is 108. No, wait. Is that right?
Yeah.
Wait, something's not right there. Oh, no, yeah, I was going to say, I screwed this up. What I screw up? Some of you already read it. Some of you know. This is wrong here. Read it again, read it again. I was going to say that
Longest side plus the girth.
longest side plus the girth. Longest side plus the girth. So on this one, what's the long side?
X.
X plus the girth. So this would be 3x plus 2y equals 108. Right? And on this one, it would be 4x, the girth, plus the long side, which is y, equals 108. So we have different scenarios. Even though it's the same thing we're trying to maximize, we have different secondary information. So we're going to solve this one for y. We're going to plug it into there. We'll have it now down to one step, so now we're below the red line. Now we'll have an equation for volume. We'll just have x's. We can do v prime, set equals 0, list of candidates, blah, 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 blah. You're now into the calculus part. Here, we're going to solve this one for y, right? We'll have a different equation there, but that will go in place of that y. We'll now have our volume in terms of one variable. Now we want to maximize the volume. How do you find the maximum of a function? You do the derivative, see where it's 0, see where it's undefined, check endpoints, do a list of candidates, justify, find the max. And so then it's going to ask you what are the dimensions of the largest. So you have to compare the two, right? This way, you'll get a certain volume as the max. The other way, a certain volume, whichever of those is the biggest, would be your answer to that question in part B. Okay, part C then is very similar, except they're cylinders. So you can have they're cylinders. Okay, so you can have a very short, flat one or a tall one there. Okay? All right. Go to work. That problem alone takes a little while. Okay? All right. You have the rest of the time to work. Answer books up here if you need to look. Fast. Sit down. Overhead, yeah.